Now let me introduce the first speaker, which is Dr. Rosa Badia from the Barcelona Supercomputing Center. Rosa is a scientific researcher at the Spanish National Research Council, and she's also the leader of the Workflow and Distributed Computing Research Group at the Barcelona Supercomputing Center. Rosa got her PhD from the Technical University of Catalonia in Spain. Between 1998 and 2008, she was working as a researcher and teacher at the Technical University of Catalonia since 1997 in the position of an associate professor. Her current research interests are programming models for complex platforms, including multi-core GPU, grid, and cloud systems. Her group has been developing superscalar programming models now for more than 10 or 15 years. And this was very successful. The programming model was adopted by many application developers. And so it's no surprise that she has published more than 150 research papers and worked, I think, on more projects that I can count. Rosa, we are very much looking forward to your presentation, and the floor is now yours.
Thank you very much, Felix. OK, so I'm going to speak today about superscalar programming models. And most of you already identify here two things, two types of ideas. Superscalar, from superscalar architecture, from the hardware architecture field, and programming models, from more software engineering, programming languages, and so on. So this makes me think about this book that I recently found out about it, which it's from Scott Bercom. I don't know how popular it is in the States. In Spain, it's not known at all. In this book, The Myth of Innovation makes very shocking statements, I think, for us, for example, because he thinks that there are no new ideas. So if you want to do research and think for a new idea, according to him, there are no new ideas, that in fact, every idea is a combination of ideas that were defined before, and that every creative thing that you can do can be split on different ideas that were there before. And if you want to be creative, this is more for not that much for research, but for creativity. If you want to invent something new, you should look at the things and try to combine them. If you take an orange and a website and try to combine things, and look for new ideas. So when I came into this book, I thought, well, maybe I can try to think what are the ideas that compose our programming model. And so I did like a kind of deconstruction of the superscalar programming model, looking for those ideas that I think that were previous in our area of research, but that somehow compose the programming model. And I choose a set of them, which I don't think that are the only ones. Probably for me, it's a valid set, but can be more extends or even more reduced, maybe. But I think it's a valid set for me. So first is high-level sequential programming. Superscalar programming is based on programming sequential applications. Programming language for sequential applications enables the expression of the algorithms, of the ideas that the application developer wants to put in the program with a simple interface, and establish a valid order of execution. So it also is a tool to describe the procedures between humans, which happens to be executed by machines. But the important thing is that when you look at the code, you can see the semantics of the problem that you want to solve. If when you look at the code, you don't understand anything, something's wrong. Okay? Regarding programming sequential or parallel, here people speak a lot of parallel programming. Maybe we can think in parallel, is this what they said, but we speak sequential, we write sequential. So it's much easier to program an application sequentially with a valid order, okay, that maybe later we can look into ways of parallelizing it. Another idea is the processor architecture. No? If you look into the processor architecture, the instruction sets, the programs in the instruction sets follow a sequential order. No? In the superscalar design, however, we come into a parallel execution of this. Why? Because we look into the dependencies of the instructions, read after write, write after read, write after write. And thanks to these dependencies, we find an order, a valid order of execution of the instructions. And we can, even we start every cycle a new instruction, eventually some instructions can get stalled and can get longer. But at the end, the important thing is that maybe we have changed the order, but we have executed them in parallel and in a valid order, and at the end, hopefully, we get a better performance. No? We can also do a speculative execution. No? Maybe we'll execute more instructions that are going to be useful, but this doesn't matter if at the end we get the correct result. No? One of the weaknesses of superscalar processors is that they can have a smaller buffer, so we can only start a small number of instructions at a time. For these new designs, like the kill instruction processor, where 1,000 of instructions can be in flight, are very promising because these enable to look for further parallelism and to execute more instructions at a time. Previous studies also in the computer architecture area, we have the data flow machines, where ideas that come from the data flow machines also have been later applied in computer architecture and current processors, and also we can import some of these ideas for our superscalar programming model. Another idea is the workflow management system. No? One observation about the workflow management systems is that workflows, we think nowadays for software workflows, but in fact this was first started on the manufacturing industry. The Ford pipeline, it's an example of a workflow that increased the performance, the production of the cars, in this case, highly in very short time. No? Or the time and motion studies that were used in science management and in the last century. Sorry. So a workflow is a graph where the nodes in the graph are tasks to be executed, and we have edges between them to denote the dependence, so we will not execute a task until these dependencies have been solved. No? And the workflow management is what it does in the intelligent engine that executes this task graph. And performs resource management and takes decisions what to better execute every time. And as you know, this is extensively used in a large number of scientific areas. Another idea that I took is the agnostic access to utilities or to infrastructures and resources. No? This is something that nowadays we are very used, no? To open and take water in the bathroom, or going and take a plug and get electricity. No? And you pay for whatever you use. No? And you don't care how these utilities are managed. Okay? Simply, you use them. Therefore, this idea is also what we take in our programming model, no? Because we use the computing and storage platforms the same way that we use the utilities in our normal life. One observation here is that we have problems sometimes with unification of the connectors, no? Of the adapters. So it's important to have standards so we can access these utilities in a transparent way. So what is the superscalar programming model? No? Taking into account these ideas that I choose, it's based on a high-level sequential programming. It executes following the superscalar processor model, following an out-of-order execution, and where the task is the unit of work. And in this case, a task can be compared with an instruction in the superscalar processor. Builds a task graph at execution time that express this potential concurrency. There are a large number of in-flight tasks, so we can look into distant parallelism and further exploit the parallelism. And then it has a runtime, an intelligent runtime, that makes decisions and executes the workflow, which is the task graph, no? And offers an abstraction to plug the applications into the resources, which is computing and storage resources. So the rest of the talk, I will speak about these different components of the Superscalar programming model framework in general. No? And if we look at this in the slide in the figure, what we want to offer is to the applications that can be focused on the problem. We want to offer an abstract level interface, the programming model syntax, that then is executed by the runtime. That it's the one that is intelligent, and should have the power to make decisions, not the application developer. And the runtime, through also unified APIs, is able to access in an agnostic way to the computing platform and storage platform. So I will be explaining a bit these different components and the decisions we made in every case. So I will start with the programming model syntax. So the Superscalar program, what it is, it's a sequential code in a regular programming language that, for the point of view of the programmer, has the view of a single shared memory space, and where we have identified the tasks. This is what we ask to the programmer, to identify those parts of the application that will become the nodes in the task graph, in the workflow, that then later we will execute. No? So the task is the main element of the programming model, no? In the computation unit, and operates on the parameters that are received and in local variables. The amount of work, the granularity of the task, is dependent. We can have, from the same idea can apply with having very fine-grained tasks to larger grain applications. An important thing also about this task is that when they start, they continue to execute till the end. And we don't consider that different tasks will be communicating during their execution, only by transferring the results to the next task. No? So for the syntax, what we need a syntax to annotate the tasks, and a syntax to indicate the directionality of the arguments, and also a way to describe synchronizations when necessary. With regard to task annotations, the idea is that we can have, for the different languages, the same idea. No? We have chosen for the different languages the annotation that better fits the language. No? In the case of C, for example, in the slide, we have an annotation for the OmpSs instance of the programming model that follows the OpenMP type of annotations, pragma compiler directives or pragmas. In the case of Java, for example, we choose a Java interface where we annotate the methods, indicating, for example, also constraints. In the case, we can say that we can add constraints to the methods. No? So again, it's an interface that it's normal in Java. And in the case of Python, we choose the decorators. That also is the way where Python programmers are used to annotate functions. No? So basically, when we add one of these annotations, we are saying that this method and every invocation of this method will become a node in the task graph. No? We can also add into these annotations, I say we can add things like constraints on the resources that will execute the task, or also hints to the scheduler like priorities or other type of hints. An important aspect of the annotations is the directionality of the parameters. There can be input, output, or in-out, which means that the task will read, write, or read and write that argument. Okay? These are used at execution time to build the actual data dependence graph of the application. So it's not that we are drawing a direct edge between the tasks, okay? Like you do when you have a workflow system where usually you have a graphic GUI or whatever where you draw the tasks and the edges. This is more an indication of the potential dependencies that you can have. And also, it's not only giving information about these dependencies, but also information about the potential locality of the data. And if there is no locality, then the data will need to be transferred if the two tasks are executed in different resources. You have an example in the slide where we are annotated, in this case in Python, two different tasks, method A and method B. Method A is writing an output, and method B is reading an input. So if we invoke first method A on a given object and method B afterwards in the same object, we will have a dependence because the object that is written by method A is read by method B. But if we invoke next method B with another object, which is not the same, this method B has no dependencies with the previous method because it's not using the same data. So this is what the runtime will do at execution time, find these actually the real dependencies between the methods. Another important aspect is the synchronization of the task. No? Ideally, we would like that we have a task graph without synchronizations and that the task can be executed with, according to the data dependencies, but without a stop. No? However, we cannot always avoid having synchronizations in the code, especially when from the code that is calling the tasks, we need to wait for a given result from a task. Okay? Then we need somehow to add a call to a synchronization to stop there till we have the result. No? It's important to understand the semantics of the synchronization. It's not only that we are going to wait for all the tasks that have been created till they are completed. Also, synchronization means data transfers, if we are executed in distributed memory, to bring data that is in another resource to the point where we are doing this synchronization. And additionally, another important point, when we have a synchronization, we stop the generation of work because we do the generation of the graph at at runtime. So when we are in a synchronization point, we stop generation of new parts of the graph. For example, in the picture, in the slide, you can see an example in the left. It's a case that happens sometimes. You have an iterative process, and in every iteration, you generate a partial task graph, and then you have a synchronization. No? In this case, between iterations, there will be no exploitation of the potential parallelism. So we will execute one iteration, do a synchronization, execute the second iteration, and so on. No? But however, if the algorithm permits to express the dependencies without desynchronization and in the form of dependencies between individual tasks, we will be able then to have potentially more parallelism and being able to exploit the parallelism across iterations, which is very interesting. No? Regarding the syntax of the synchronizations, we have also tried to follow similar standards that we have in the different languages, no? Like in the case of C, again with the pragmas. Or in Python is an exception. We could not use the decorators. We need to add a small API, but the small API it's with two different primitives, so it's really small. No? And in the case of Java, it's even better. The programmer doesn't need to add the synchronization points. By means of interception, we find the points that we need to have a synchronization. I'm going to give an example that comes from the Neuroscience Data Processing area. It's an example that computes cross-correlations between data of spikes of neurons. This example is taken from the HPP project that we contribute. Also, besides computing these correlations between spikes, also computes correlation between surrogate data. So it's a very highly parallel application. No? I don't want you to read the code. I will point out what I want you to see in this code. No? This is have two loops in C, in Python, sorry, that does the cross correlation between all the data in the different neurons. No? And also we have an inner for no, that does the cross correlation with the surrogate data. And this is the sequential code. The programmers at the beginning in the project were using parallel Python to parallelize this code. An important thing here that we see, we have explicit declaration, explicit access to the resources. Okay, I cannot point it. But if you look at in the slide, you can see that we are looking into the actual resources where this is executed. Also, then we are doing explicit fork join the distribution of the work. And also, we can get the data back explicitly at the end. No? So here, it's an example of the code of what we would like to avoid, that the programmer have to take into account where it's executing, the different synchronizations, and everything. This is the same code now in PyCOMPSs, which is the version in Python of COMPS, one of the instances of the programming model. As you can see that it's much more simpler, very close to the sequential case. We have annotations in the right of the tasks that the application has one task, the CC surrogate, that computes for a block of data and another block of data, the correlation. So we split all the sets of correlations in different smaller blocks, and we invoke tasks that do these correlations for the different blocks. And then we have a task gather that gathers the results of the previous computations. The task graph that is generated is the one that we show in the slide. This is a smaller version, but you can see it has some tasks that can execute in parallel and others that are sequential, but thanks to the runtime that can prioritize tasks and interleave the task's execution, there is not a bottleneck at the end. So then I'm going to go into the runtime. So this is the runtime behavior. I would like that, as Alan Aldal was saying this morning, this is like one of the important parts to understand. If you understand how this works, I will be happy. So we start with the user code with these annotations that I was showing you, and then we can compile, or by means of interception or interpretation, whatever, we add calls to our runtime. Okay? So every time we call a task, the runtime will add a node in the task graph, and we'll look for the dependencies between that task and previous tasks that have been called. So we will have a partial task graph. Once we have this part of the graph, we can start looking for the tasks that can be executed, and we assign them for the execution in computing resources. These computing resources can be cores of the multi-core, or can be nodes in a cluster, or can be nodes in a cloud. If these tasks that we want to execute requires a given data, also the runtime will make the necessary operations to move the data, if necessary, to the node, to the place where this task has to be executed. Of course, there will be policies in order to reduce the amount of data that travels between nodes or between different spaces of memory. So the runtime has different features. So it's the important part for us of the programming model. It has this dynamic task graph generation, implements things that we have reused from processor architecture, like data renaming, performs the scheduling, if necessary, the data transfers, resource management. Also, to improve the resilience of the applications, can implement fault tolerance and checkpointing mechanisms. And also, it's the interface into the computing and storage platform. In the slide, you have the architecture of the COMPS runtime. But it's not, in this case, I don't want to explain the runtime, this runtime itself, but the fact that it's based on components. So we design these runtimes with different components, and each component has a specific task. For example, we have, in this case, an engine that adds the tasks into the task graph and performs the scheduling. One part that does the resource management, and another part that does the integration, adaptation with the storage and computing platform. I've talked a bit already about the task graph generation. We do on-the-fly creation of the task dependence graphs. So for every task invocation, we add a node in the task graph and look for the dependencies. Different input data can generate different graphs. So the same application with different input data can generate a different graph. And also, from different applications, we can have very different graphs. With data renaming, we can increase the parallelism. It's a technique from computer architecture where you do versions of the same data that is going to be reused. In the slide, we have these dash dependencies between the part of the task graph and that are reuses of the same data. So if we do a copy of this data, we can further increase the parallelism of the graph. But renaming can be expensive. That's why you have to implement smart techniques or lazy renaming techniques to renaming in order not to exploit or use the memory too much. No? And scheduling will start as soon as some task has been generated in the task graph. Task scheduling, well, I can speak the whole talk about task scheduling. No? You can have very different alternative strategies. You can have a centralized scheduler. You can have distributed in the worker nodes that steal the tasks. Important things here, no? The impact of the scheduling. It's not only about making a good decision on the task that you think that's going to get the best performance or less time. Also, it should take into account aspects such as the locality exploitation, no? Because we are here, locality is not only thinking about the closest levels of the cache memory, because we are talking about tasks that can be executed in different nodes in the cloud, for example. So we have a large number of alternative policies, from very simple ones, FIFO policies, traversals of the graph to exploit concurrency, locality aware, priority aware, criticality aware, no? Look into the tasks that are more critical in the graph and try to execute them before. Or other things like energy aware, where also the locality can have a lot of impact here. No? So the runtime also implements this interface with the computing platform. No? And here I'm comparing two different implementations to see that, in fact, it's not that important if you're working in one platform or the other, but the ideas are basically very similar. No? So in the case of the cloud computing, we have a unified access to different cloud providers. And the problem here is that different cloud providers, especially the public ones, have different APIs. No? So then what we have designed is a connectors interface that we call, which is always the same interface that the runtime sees. And then we have different connectors for the different providers. Here, an important thing is, well, to have standards. For example, OCCI is a standard from the cloud community that can be then used for OpenNebula or OpenStack or in the European AGI federated cloud. With this interface, we can work from the runtime into different public and private clouds at the same time, using the same interface. In the case of the heterogeneous computing, we have a similar idea. From the Nanos runtime, in this case for heterogeneous computing, we have also an architecture interface that then can have different components specific for the different platform devices, no? For multi-cores, for GPUs, for the mic. In this way, from the Nanos runtime, we can execute tasks using the same interface at the same time in multi-cores, in GPUs, in the mic, and so on. Another example that similar techniques that can be applied in different worlds is in resource management. No? The idea of elasticity in the cloud. When we use elasticity, when we have high demands for an application of computation, and we create new VMs in a cloud, can be public or our own cloud. No? And when we don't need them anymore, we will delete the VMs and continue the execution. The same idea, if you look into heterogeneous computing, when we have threads in a node, several applications can be run in a node sharing these threads. No? When one of the applications need less threads, can be used by the other application, can be lent to the other application that can, at that moment, use more threads to finish the application. So this is a way, for example, for balancing the load of MPI plus OmpSs applications at execution time. No? So with regard to the computing platforms, I wanted to speak a bit about the different implementations that we've been doing during the year. No? So we started with the Grid. Grid Superscalar was the first instance that we developed and was maintained approximately till 2011, and was enabled through Globus Toolkit and in the grids, but in the clusters, we can also run in the clusters what used with SSH. Was in production in Mare Nostrum, so this allowed us to have quite a significant number of users, and we get feedback from these users that was very interesting. So here, a characteristic is that the tasks were with high granularity, no? From order of simulation, so on, and the objects that were exchanged between the tasks were files. Another example is the cells processor. No? I guess you remember the cell processor had a cumbersome architecture and with all of the elements that fit the programming model. If you look at the cell processor, it was also like a grid, no, at a smaller level. So we had this PPE, it was quite a slow processor with 2 threads, and then the SPEs that were the powerful processors. No? An important aspect here is that this processor didn't share the memory, so you had to do transfers between the PPE and the SPE. No? And so we implemented Cell Superscalar. It was presented in Tampa in Supercomputing 2006. And in this case, the tasks were very fine granularity, and the operations were operating in blocks. And so we move into the current implementations. OmpSs is one of the implementations that BSC right now maintains for heterogeneous clusters. It supports multi-cores, GPUs, FPGAs, and combinations of them into clusters. It's also called that it's a Forerunner for OpenMP. It's where we develop new ideas and try to promote them into the standard. The variability of the task here can depend, because if it's not the same a task that needs to be run in a multi-core than a task that needs to be run in a GPU, or nested tasks that can be delegated into the nodes of a heterogeneous cluster in the case of the at-cluster implementation. Similarly, with the blocks, the objects can have also different size depending on the actual tasks. No? Another characteristic of this implementation is that it hybridize very well with MPA, and here the idea is to have MPA between nodes to parallelize the application on the cluster, and inside the node, use OmpSs to parallelize inside the nodes, but also with the objective of overlapping computation and communication. In general, this version has a lot of interoperability with CPUs, GPUs, the mic, and leveraging CUDA, OpenCL, and edge streams for the mic. For the cloud, we have this COMPS implementation that runs both in the cloud but also in clusters, and offers interfaces for Java, Python, and C, with also, again, variable granularity of the task. No, it's not a task that has to be in the cloud than a task that runs in a cluster. And another characteristic here is that the tasks can be web services. Here, the objects can be both files or objects in memory, can have both cases. And one of the strong aspects here is the interoperability that are supported in the cloud environment. So we support federated clouds and different middlewares of clouds. This is ongoing work. This is not available, but it's to see what we are looking into. For example, we have this mobile implementation, COMPS Mobile, which we are porting the runtime into an Android. And then the idea is to offload the tasks into nodes in the cloud. Here, for example, one of the challenges is the unreliability of the network. So we have to support disconnections between the master and the tasks. In this case, also, we can consider the execution of some of the tasks in the processors of the mobile, which every time are more powerful. No? Then we can have variable granularity of the tasks, depending if they are executed in the mobile processing units or in the cloud. And objects, again, can be files or blocks in memory. Here, another challenge is the use of the energy in the mobile device, that you can imagine that it's also a sensible aspect. So I'm going now to move into the final section, which is the storage platform, how we address the access to the storage platform. No? So the general model is that stars is a sequential code that, from the point of view of the programmer, it's accessing a single address space. However, when executing, as you have seen, we can be addressing larger spaces of memory, distributed. And this larger space of memory is made available for the programmer. So from the application can be using larger amounts of memory. And then the runtimes deal with the management of these separated spaces, with data transfers, location of the data, where each object is located, coherence, whatever. And it's a very good candidate for big data applications due to this characteristic, and also because of the flexible programming model that is offered. No? Then we have the challenges from the storage. No? We have new type of devices, and VRAMs, storage class memories. These devices resemble more memory than storage, no? Because you have low latency, high bandwidth, and byte addressable interfaces. No? So it seems that devices where it will be more logic to store the data as objects more than in the traditional file system way. No? And then also together with the new requirements that we have from big data applications that have large amount of data that is generated by simulations and other applications in general, and the fact that moving the data is very expensive, we are looking into new requirements like in situ processing, new type of problems. No? So at BSc, there are different initiatives to exploit this type of storage. For example, DataClay, it's a library oriented to persistent objects. And so it's an object-oriented library where the objects are persistent. So when you finish the execution of the task, they will be there available for the other users. No? And also it adds that other users can enrich the objects with new methods, or you can specify privacy or security into these memory objects that are now there. No? Another work by my colleagues is Cuba, which works right now with the Cassandra databases. And this defined set of operations to better locate and manage data in Cassandra clusters. And that's a nice interface with Python. It's mapping Python tables, Python dictionaries into Cassandra tables in a very transparent way. And doing things like redefining iterators in order to use iterators in the Cassandra databases. So we had these different initiatives, and they say, okay, we would like to integrate the programming model with this new initiative, but we don't want to do an implementation each time, so we designed a single API to interface with these different implementations. No? So this API defines ways of defining parts of the code of the programming model, in this case of the COMPS implementation, defining objects that can become persistent for the applications. No? Basically, the more important concept is this one, making persistent some objects, and then managing from the runtime the location of these objects in order to make decisions on scheduling or making versions, replicas, and so on. So the idea of using COMPS and data persistency would be, for example, in this case, we have a producer application that have a couple of objects, and the application can decide to make one of these persistent. No? So not all the objects need to be persistent. We can have some objects that are persistent and others that are not. So when we make an object persistent, we can have tasks operating in them, and other consumer applications that can operate also in this persistent data. So we made the objects that are persistent available to other tasks from other applications. And well, this is again, to recall the example from neuroscience. We can use this to make the neuron data, the spikes, can be considered as persistent before the execution of the application. We can make them persistent. You can see the call to the make persistent function in the call. And when we iterate over the blocks of data, we have redefined the iterators to be working on blocks of data. And these blocks of data are then assigned to tasks. So here you see how it integrates everything. No? The blocks of data then are in the same location of a Cassandra node, for example, and then the task will be executed in that single task. No? So it's the way that we have to exploit the locality of the data inside the node. So well, this is still ongoing work, but I think that this is very important for our group, very promising. We are looking forward to this work. So then for concluding, the key points of the Superscalar programming model, it offers a single syntax for sequential programming. It's based on the task graph that express the semantics of the application's behavior. It's important, this idea, that the runtime is the one that makes the decision. No? We give the power to the runtime. And offers also a layer that makes the applications agnostic of the platform. We have seen different implementations that we've been working on that validate the applicability to different areas from HPC to cloud. And that's also a very good candidate for other areas like the convergence of HPC with big data. And we see also applicability in the mobile cloud or for computing of these areas. We have been very active in different projects. Probably it's not complete the list, but these are some of the projects that we have doing some kind of development or technology transfer with the different versions of the programming model. And also, of course, another of the things that says Scott Bercombe is that there is no single inventor, no? That always it's a group of people that works in new things, no? And as you see, it's a very long group of, I hope I didn't forget anybody, but it's a large team working on these programming models. And also another thing that says Scott Bercombe is that there is no epiphany ideas, no? So it's not the ideas appear and then they succeed. You need to implement prototypes to validate them and to use them, no? And here we have releases of both the now implementations that we have. COMPS was released version 1.3 last week. It's available in the website, and you can come to our booth and see demos. And the same for OmpSs. It's available for everybody, and you can get it from the website. Thank you.
Yeah, thank you very much, Rosa. Do we have any questions? So as I said, you can either use the microphone or use the C15 app. I have already one question on the app, Rosa. How do you handle dynamic dependencies in your syntax?
Okay. How do
you handle dynamic dependencies in your syntax?
Well, the dependencies are not are defined at runtime. We look for the dependencies, looking at the actual data that is used. So, for example, some implementations will use the actual address in memory that the object is accessing, and if the address is the same, we'll find out that it's a dependence. And in other cases, it's a handle that describes, depending on the language, the dependence will be identified on different ways.
Okay. So we have time for one more question. Does anybody have a question?
Yeah. There is.
Oh, yeah.
Hi, Benoit Meister from Reservoir Labs. I was wondering about the schedulers. How do they make their decisions? You've told us about different strategies they have. Do they do a partial graph construction and then analysis, or do they take input from the users? Like I know that other runtimes use hints like concurrent collections and OCR, for instance.
There is a bit of everything, no? There is information about the tasks that are ready, and then depending, nice things we have is, for example, on the OmpSs runtime, is that the scheduling is pluggable, so you can decide for one policy or another, no? You can decide for a very simple policy that will be very fast, or you can look for more smart policies. For example, in the heterogeneous case where you have GPUs and CPUs, you need to use more smart schedulers because locality there, for example, is very important. No? In some cases, we have hints from the programmer that indicate that a given task has a priority. But it's not enough with knowing that this task has a priority. If you don't propagate this priority in the graph, you will not really prioritize that task, no? Because if you have a parent of this task that doesn't have prioritization, you need to propagate it up, no? And this is something that we need to do, no? We need to traverse then the part of the graph that is available to propagate the task. No? In the cloud implementation, also now recently we have implemented this pluggable interface. But right now we have only a couple of schedulers, one which is very simple that basically schedule the tasks first in, first out, and a second one which is energy aware, so takes into account the energy that the different tasks use and in the different VMs of the cloud. And according to this, we'll try to model the use of energy in the different VMs and try to make better decisions, for example.
Okay, thank you.
Thank you.
Okay. Yeah, thank you very much again.
Thank you.